This is lesson 88, VHDL example 59. In this example, we'll write a VHDL program that will display the Fibonacci sequence on the 7-segment displays. Here's the beginning of the Fibonacci sequence. It starts with 0 and 1, and then each subsequent digit in the sequence is the sum of the previous two digits. So 0 plus 1 is 1, 1 plus 1 is 2, 2 plus 3 is 5, 3 plus 5 is 8, and so forth. Now the Fibonacci sequence has a number of interesting features. One is related to the golden rectangle. Golden rectangle is one whose sides A and A plus B are similar to a rectangle you get by squaring the original rectangle. That is, you make this a square of side A, and then the ratio of B to A of this smaller rectangle is the same as the ratio of the A to A plus B, the smaller to the longer side of the original rectangle. If you cross multiply here, you'll get A squared equals AB plus B squared. If you divide by A squared, you'll get 1 plus B over A plus B over A squared, call it F. And then if you solve this quadratic equation for F, you find that the ratio F is 0.618034. And if you look at the Fibonacci sequence, which I've listed over here, and if you take the ratio of adjacent numbers in the Fibonacci sequence, you have 1 divided by 1 is 1, 1 divided by 2 is 0.5, 2 divided by 3 is 0.66, 3 divided by 5 is 0.6, and so forth. If you keep going, you see that by the time you get down to here, the ratio converges to 0.618034. That is the ratio of this golden rectangle. Now, here's a circuit that we can use to compute the Fibonacci sequence. We want to set Fn to 0. That'll be the output, say, of this register, and Fn1, the output of this register, to 1. So we'll start with 0 and 1, and then we want to update the Fn and Fn plus 1 as long as the output Fn1 is less than 9999, say. And then we'll cycle back through. So we need the sum, so we take Fn, Fn1, we add them, call it Fn2, and that's going to be the new Fn1. So the new Fn1, which is going to be Fn2 now, will be Fn plus Fn1. So on the next rising edge of the clock, this one will get the sum, and the old value in here then goes into Fn, which becomes the new Fn plus 1. So the output, which will be a 14-bit number, will be the Fibonacci sequence, which will continue to go on each rising edge of the clock. Now it turns out that we can write a VHDL program, we'll call it Fib, to do this in a simplified way. We got clock and clear, and F is going to be the 14-bit output. This is the architecture for our VHDL program. We'll define signals Fn1 and Fn. These are going to be the 14-bit outputs of our two registers. We'll define a constant equal to 9999. Then in this process, with sensitivity lists clock and clear, if clear is 1, we'll initialize the output Fn to 0 and the output Fn1 to 1. Then on the rising edge of the clock, we'll check to see if Fn1 is less than 9999. If it is, we'll update the two registers. Fn1 gets its current Fn1 plus Fn, and Fn gets the old Fn1. So we use these two instructions to update the two registers. The plus sign will implement the adder automatically here. When we get to 9999, we just reset Fn to 0 and Fn1 to 1, and the sequence will start over again. At the end, we'll take the output F and set it equal to the signal Fn. Here's the simulation for fib. Here's the output F. So on every rising edge of the clock, it counts 1, 2, 3, 5, 8. D is 13. Hex 15 is 21, and so forth. So it's counting in hex the Fibonacci sequence. Now to display it on the 7-segment display, we'd like it to be displayed in decimal. So we'll add our binary to BCD 14. Here's our fib. We'll bring our clock 3, our 3 Hertz clock in, so it'll increment about every third of a second. And then we'll display it on the 7-segment display. So that's the top-level design. Here's what fib top would look like. We've got M clock, button in, 3 down to 3, that's our clear, and then the A to G, A in, and decimal point out for the 7-segment display. We've got our component for clock div, our component for our binary to BCD 14, our component for fib, our component for X7 seg BC, and then we've got the signals clear, clock 190, clock 3, P and B. P's 16 down to 0, B's 13 down to 0. Then clear will be button 3, and then we just port map clock div in the usual way. Port map fib, clock goes to clock 3, F goes to B. Here's binary BCD, port map B to B, P to P, and the X7 seg BC. So you can download this top-level design to your FPGA board, and when you run it, the Fibonacci sequence should be displayed on the 7-segment display.